Now you know that alkenes react by addition because they have this pi bond which is relatively weak, and so it tends to get broken and the electrons get used to make new sigma bonds instead. So all these reactions with bromine and with hydrogen chloride and with hydrogen and with steam, all of these things follow that same pattern. Now there is another way that alkenes can do the same thing, which is to break open the pi bond, use the electrons to make new sigma bonds. But rather than reacting with something different, they can react with each other. And that process is really important industrially because it's used to make polymers, which in everyday life means plastics like polythene and polypropylene and various other things. So we need to know a bit about that. So the simple way to visualize it is if you imagine a pair of alkene molecules like this. Now what I'm going to draw is not really the mechanism of the reaction, but it's just a way of visualizing how polymerization can come about. So we've got a pair of alkene molecules like that. Now suppose the pi bond breaks, and if we break it homolytically, which remember means the carbons get one electron each, we'll get that. Now this alkene could do the same thing. So again we break the pi bond and generate one electron on each carbon like that. So if these two molecules meet, then you can see that what could potentially happen is that this carbon with its one electron could see this carbon with its one electron, and they can see that they could pair those electrons up to form a new bond between the two. So we can draw that out like this. And let's draw the new bond in a different colour. So you can see that's what used to be these two separate electrons, and those, remember, came from the pi bonds that were broken. So on this side we'll have this. And so the important thing is, first of all, we've now joined two molecules together to make a bigger molecule, courtesy of that new bond formed there. But the second thing that's important is that at each end there's still an unpaired electron. And of course what that means is that if another alkene molecule now comes along, like this, it can do the same thing. So again, we can break open the pi bond like that and form an unpaired electron at each end, and again this one and this one can pair up to form a new bond. So we'll just write this out one more time, and then hopefully you'll see that this process can go on and on following the same pattern. So we've got this that we already built in the first step, but now instead of just having two molecules together, we have another new bond here joining a third molecule on, and so we get this. And again, you can see that there's no reason for it to stop there because you've still got an unpaired electron on each end, so you can bring another alkene on and another one and another one. And in this way you can build up huge long chains, you know, of hundreds, thousands of alkene molecules joined together to make really big molecules which we call polymer molecules. So that's the principle of polymerization. But as I say, this is just a general introduction. What we need now is to represent this a little bit more formally. So let's start with ethene again. And what we're going to do is to say that in order to make a polymer, we need a very large number of these. We can't specify how many, because the polymer chains won't all have the same length, so we can't say specifically, you know, 3,709 of them are going to polymerize. All we can do is say it will be some large number that will polymerize together to make each chain. So we're going to use n to represent a big number. And then we can say, right, what happens as a result of that? We can summarize by just stating what happens to each individual monomer, each individual small molecule that went in there. So those two carbons across the middle will now just have a single bond in between them, because remember we've broken open the pi bond to make the new bonds possible, and here are the new bonds formed at either end. These are the ones that weren't there before, and these will link onto the next unit that's added on each time. Meanwhile, the 4 hydrogens that were on the corners there are still there, because it's an addition reaction, nothing is lost, so whatever goes on these 4 corners, in this case 4 hydrogens, will still be there. And then what we can do is put a bracket round this, and when you draw that, the important thing is the bracket must slice through the bonds like that. And this is now called the repeat unit of the polymer, because what the actual chain consists of is that just repeated lots of times, and specifically if n of them went in, then it's repeated n times, so we put an n down there to mean that's the number of these repeat units in the polymer chain. So that's an equation for addition polymerization. Now the words that go with that, this is called the monomer. Okay, so monomer is what the alkene was before it reacted. This, on the other hand, is called the repeat unit of the polymer. Okay, so don't get those two things mixed up. The monomer is what it was before it reacted, and the repeat unit is what each individual monomer becomes after it's reacted. And so that's what you've got there. So you can write that as an equation, and that's fine. If they ask you to draw the repeat unit, you can just draw that. Sometimes they ask you to draw several repeat units, 2 or 3, and that's easy to do because you just basically string 2 or 3 of these together, all joined up through these linker bonds. So 3 repeat units of this. Here's our first one. And here's our second one. Let's do it in a different colour just to illustrate that these really are repeats. So here's the second one, exactly the same, just joined up by that new linker bond that we created. And then here's the third one. So that's 3 repeat units. That's just like a snapshot of a bit of the polymer, because there would be hundreds of thousands more of these, but all joined up in the same way. So if they ask you to draw 3 repeat units, that's all you need to do. You can put the brackets in as well if you want to. You don't have to, that would be perfectly fine. But if you want to, if it just helps you convince yourself that you've got it right, you can put the brackets in like this around each individual repeat unit. So that would also be fine to show 3 repeat units, but you must show them linked together, and the linker bonds must slice through both of those brackets if you draw the brackets in. Now obviously ethene isn't the only alkene that will do this. In principle any alkene can do it. So for example, if we take this compound, which is propene, then it can follow exactly the same pattern. So we can have n of those joining together, and the repeat unit is always easy to draw because you just think, right, these 2 carbons, the ones that were double bonded originally, they go across the middle and they will join together to make the long carbon chain, and then the 4 things hanging off it are still hanging off it in the repeat unit. So you just put the same 4 things on like that, and that's your repeat unit dealt with. And on it goes, you know, so that will be repeated n times to give you the polymer. Now you can name these polymers very easily, because we've seen, for example, in this case, that this is propene, and you name the polymer just by putting poly. Poly just means lots of, so poly, and then in brackets the name of the alkene it was made from. So that's called polypropene. And some of these sound vaguely familiar. So if ethene polymerizes, it makes polyethene, which normally gets spoken as polythene, which is obviously very familiar. This one is polypropene, but again the old name for propene was propylene, so polypropylene, which again you've probably come across. So these are very important familiar compounds that you can make in this way. So the other thing you need to be able to do is if they give you a snapshot of a bit of polymer, you need to be able to work out what the monomer was that it was made from. So for example, if you have, let's do something slightly more exotic. Suppose you have this. Okay, so this is just an example of a polymer that could exist, and again we've just got a snapshot of it, just containing a small number of repeat units, but remember it would really be much longer than that because these linker bonds on the end tell you that the chain continues in the same kind of way. And if they ask you what's the monomer that that's made from, then the easy thing to do is just draw a bracket around the repeat unit, and that's easy to do because you know it will just have 2 carbons across the middle. So you can straight away say, right, that's going to be the repeat unit, and you can see that's true because what comes next with the H and F there is the same as the first one in the repeat unit. So you could obviously draw enough brackets there and there, but that's all you need because you say, right, that's the repeat unit, and so you can say, right, the monomer that that's made from would have a double bond across the middle instead of the single bond, but the 4 things in the corners are the same. So you would have that as your monomer. So you just need to be able to go in either direction like that. So here's another example. Again, this is a snapshot of a fragment of a polymer chain. So again, you can easily work out what the monomer was by drawing the bracket around the repeat unit like this and saying, right, okay, that's going to easily tell me what the monomer is because those 2 carbons become these 2, and then we get H and H and H and CH2 CH3, so it's but1ene is the polymer. So this is polybut1ene is the name of the polymer. Now, one of the kinds of questions they sometimes ask you is they say that this has a mean MR of let's say 42,000. A mean MR because not all the chains will actually have the same length, so individual molecules will have different MRs, but if we work it out averaged over a mole, then we get 42,000. And they might ask you, what's the average length of the chain? So what you do is you say, right, well that has an MR, if you add it up, of 56, and so you say that therefore the number of repeat units in the chain, or if you like the number of monomers that join together, is just equal to the total MR, 42,000, divided by the MR of each individual repeat unit. And obviously the repeat unit has the same MR as the monomer because it's an addition reaction. You don't lose any atoms, so each of those repeat units still has an MR of 56. And if you do that, you get, I can't remember what that is now. Let's try to work this out in advance. 750 is the answer. Okay, so 750 repeat units in the chain. So those kind of calculations are quite easy, but they're also quite common. The final thing about these addition polymers is that you need to know a little bit about the sort of real world issues around using them. So the big problem with them is that they are non-biodegradable. What that means is that bacteria, things like that, which normally will break big molecules down in the environment back into small molecules, which can then go back into nature in various ways to be made into new things. That doesn't happen with addition polymers because the bacteria have no enzymes available for catalyzing reactions which would break these things down. So what that means is that they don't break down into small molecules in the environment. And so if we chuck them away and just bury them in the ground, they will stay there indefinitely. So they accumulate for very long periods, possibly indefinitely, in landfill if we chuck them away. So you need to be able to explain that that's a problem, and you also need to be able to suggest what the solutions to the problem are. The obvious one is recycling, and obviously that's done on a big scale. There's not really much sort of chemical to say about that, but it is, I guess, the best answer to the problem. But there are other possibilities, so we'll just mention that one, but we won't really say any more about it. The second is combustion, because these long chain alkene polymers are basically they're just alkanes, they're just long chain alkanes. So like other alkanes, you can burn them as fuels. Okay, so use as fuel to produce energy, e.g. to generate electricity. It's always important you say why combustion might be a good thing, so don't just say burn them and then don't clarify why that would be a good idea. So explain that by burning them you would potentially have a useful fuel, e.g. to generate electricity. But the problem is that toxic gases may be produced. It depends on what your polymer is, but they tend to undergo incomplete combustion, so you get various hydrocarbon products forming, some of which may be toxic. Perhaps the most obvious example is if you have chlorinated polymers like PVC, which contains chlorine as well as carbon and hydrogen. Then when those burn, it tends to produce HCl, which is very toxic and also acidic. So, and a good example of that would be HCl from chlorinated polymers. And that can be dealt with, these things can be dealt with, so they have to be removed from the waste gases to make sure they're not released into the environment. But that's a possible way forward. The other thing that you could do is to break them down chemically. So we can't rely on bacteria to do it, but we can use an industrial process to do it. And if you think about it, these polymers are just long chain alkanes, or sometimes chlorinated alkanes, but basically they're just like alkanes. And so you probably know from GCSE about cracking, which is a process which breaks long chain alkanes down into shorter alkanes and alkenes. And so you can do something very similar to these, and that will generate more small molecules, for example more alkenes, which you could then use to make more polymers and so on. So in general terms we could say break down chemically and use the small molecule products as a feedstock, is the word that gets used. Feedstock just means the chemicals which are fed in to various processes for making other useful chemicals. So use the small molecule products as a feedstock for making other organic chemicals. And that may become an important way forward in the future as well. So you just need to be aware of these possible things that you could do with polymers. And you also need to be aware of the fact that there could be a sort of radical alternative to all of this, which is to stop using addition polymers and instead to use polymers which are biodegradable. And that's something we'll learn more about, not very much more, but a little bit more about next year, that there are other types of polymers, some of which will actually break down in the environment, and that of course could be a completely, radically different way of doing things.